So for lesson 5, we have 3 different objectives. The first is to be able to define, recognize, and notate sets, and in particular 3 specific sets, which we will talk about. The second is to be able to determine absolute values. And the third is to be able to apply the commutative property for addition. So starting with sets, around here. So a set is a well-defined collection of numbers, objects, or things. And for the purposes of our class, we're really going to focus on collections of numbers. Okay, so this could be any well-defined collection of numbers. So for example, we can have a set of positive even numbers. So that would be 2, 4, 6, 8, etc. We recently have been dealing with natural or counting numbers. And so that is the first set that we're really going to need to remember for this class. Here's how we notate a set. So we've got a bracket here and a bracket. So brackets on either side. And then for natural or counting numbers, we remember that these are the numbers that we count with. So we start with the number 1, 1, 2, 3, 4, 5, 6, 7, etc. You can just notate a handful of them. And then this is really important. We need to include this ellipses here, this dot, dot, dot. That indicates that this set stretches on infinitely, okay? Because we could theoretically count forever and never come to the end of this counting set, okay? So make sure you include that dot, dot, dot. Next up, whole numbers. And whole numbers are the counting numbers. We just add the number 0 to the set. So for the set of whole numbers, we start with 0, then we move to 1, 2, 3, 4, 5, however many you want to write. Include that dot, 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 and close it out. The last set to remember is our set of integers. So this now takes our whole numbers, and then it adds the opposites. So it adds the negative numbers over on the other side. This one, we actually start with an ellipses, because the negative numbers, like if you look on a number line, the negative numbers also extend out infinitely. That's what these arrows indicate, is that the number line stretches out infinitely in both directions. So for our integers, we'll start with that ellipses, and then you can pick whatever number you want to start with. I chose -3, but if you wanted to start with -4 or -2, that would be fine also. So -3, -2, -1, 0, 1, 2, 3, and again, that dot, dot, dot ellipses going on forever. And so those are our integers. So those are the 3 sets to commit to memory for right now. And then just understanding that a set is a well-defined collection of, we're going to focus on numbers for this class. Moving on to absolute value. So the definition of an absolute value is that it's the distance from 0 on a number line. So if you remember, we were talking about real numbers and saying that a real number is a number that can measure a physical distance on a number line, a distance from 0. And then the absolute value is going to just define what that distance is. Okay. So you can see here, absolute value, this is how we indicate it with these straight lines on either side. So this reads as the absolute value of 0 is equal to 0. That makes sense because the distance from 0 to 0 on a number line is, of course, 0. This says the absolute value of 5 is equal to 5. So you can see here I put a dot on 5 and on 0, and that distance from 0 to 5 is equal to 5. So we would say the absolute value of 5 is equal to 5. The absolute value of -5 is equal to 5, positive 5, because it does not make sense to say that a distance is negative. Okay, we don't have negative distances. We wouldn't say like, I drove -10 miles, right? So distances are always going to be positive, which is why the absolute value of -5, that distance from 0 to -5, is equal to 5. Okay, a couple sample problems here. We've got the absolute value of 11 minus 2. So whenever we see a problem like this, we're going to want to first solve what is within the absolute value symbols, and then finish from there. So we're going to first do just what's inside. 11 minus 2 equals 9. And we're going to write that this is equal to the absolute value of 9. And now the absolute value of 9 is equal to 9. And that's our answer. Over here, we've got the absolute value of 2 minus 11. So we're going to go ahead and do the 2 minus 11 is equal to -9. So we've got the absolute value of -9. that is equal to 9. So that is our answer there. Lastly, our commutative property for addition. This states that any real numbers, any group of real numbers that we have that we need to determine their sum, it does not matter what order we add them up in, we will still get to the same result. Okay. So for example, let's say we needed to add 1 and 2, okay, very basic example. It doesn't matter which order we use. So we could do 1 plus 2 is 3, or we could do 2 plus 1 is 3. And it's going to be the same answer. For a more visual example, let's say we've been dealing a lot with perimeter, right? So perimeter is we have to find all the side lengths of a shape and then add them up, and that gives us our perimeter, the measurement of the distance all the way around. So once we've determined our side lengths, we can add those side lengths up in any order, and we're going to get the same result. So like for this example with a rectangle where we've got side lengths of 5 and 2, we could say, okay, 5 plus 2 is 7, 2 plus 5 is 7, 7 plus 7 is 14. We could say, okay, 5 plus 5 is 10, and 2 plus 2 is 4, 10 plus 4 is 14. So whatever order we go in, we're going to get the same answer, okay, which makes sense, right? Lastly, I think you guys can see this from here. Okay. Lastly, we're going to have problems that look like this, where we've got a sequence of numbers and we're supposed to determine their sum. And we're going to, for right now, we're going to use a number line. And this kind of helps us to illustrate this commutative property. So I'll show you how this works. This has us starting with -4. So I'm going to start at -4 on my number line. And I'm kind of going to go up so you can see this a little better. Then it says plus, and this says +2. Okay, so when we're adding a positive number, we're going to move to the right on our number line. So I'm going to go to the right by 2 places, 1, 2, and now I'm at -2. Now it says plus -1. So when we add a negative number, we're going to move to the left, and it says to go to the left by 1. So now I'm over here at -3. Lastly, it says to add +5. So that means I'm going to move to the right by 5 spaces. 1, 2, 3, 4, 5, and I end at +2. Now, let's try adding this up in a different order just to check that the commutative property works. So I'm going to start, I'm going to choose this at random. I'm going to start with -1, and then I'm going to add +5, and then I'm going to add +2, and then I will add -4. Okay. Start at -1, and then I'm going to add +5. So that means I'm going to go to 5 places to the right. 1, 2, 3, 4, 5, 4. Now I'm going to add +2.
We have all high school volleyball, middle school volleyball, and high school football to the gym, please.
And then lastly, I'm going to add -4 by moving 4 places.
To the gym. Thank you.
4 places to the left, and awesome. I ended exactly on the same results of 2, proving that the commutative property works. Any group of numbers that I have and I need to find their sum, I can add them up in any order and get the right answer.